Hi, this is Muhammad Nadeem Asghar. The topic of today's presentation is modeling and simulation of an efficient solar power plant using maximum power point transfer connected to the main grid in Pakistan. This research article is prepared under the supervision of Dr. Mohsin Jameel, and this is a semester project to the course Grid Integration of Energy Systems. So before moving ahead, I would like to give an introduction of the topic. So it is the design and the development of a solar power plant which has a capability to generate the maximum power from the PV cells and can operate as a standalone power plant and in the interconnection of the main grids. So it can run in parallel to the grid and so it can also supply the power as a net metering solution. Before moving on to the actual project, so I would like to spend some time on the introduction and the background of the situation, which actually compelled me to think about this project. Pakistan is a nation of around 226 million people, and the population is on the continuous rise. And to feed that population, country is continuously striving to pull more industry so that the people of Pakistan can have enough resources to manage their lives. So it means so we can say that more people and more industry means more demand of electricity. In this recent situation, and the numbers of last year are saying that in 2021 the power demand was 34,501 megawatt, and Pakistan's electricity production is mainly relying on imported fuel. So it's around 59% of the total energy mix, which is coming from the fossil fuels. The fossil fuel is actually imported from neighboring countries like Saudi Arabia and Qatar. Which actually puts the country's economy under huge pressure. The import bill is dominated by the fossil fuel, and recent situation is also the evident of the economic crunch which is Pakistan is facing because of the rising import bill, because the country does not has its enough resources to purchase the fossil fuel from outside. So it is a big problem right now. If we talk about the last year, though the circular debt to the independent power producers, the country was liable to pay around $13.6 billion to the IPPs, which is even more than the current reserves of Pakistan. Uh, so so this is something, an economic reason, which is not viable and sustainable for Pakistan to carry on what they are doing now. And the other thing is the global warming. The environment has been badly damaged because of the pollution. So recently, Pakistan has seen a devastating situation in flood. It was around 33 million people who has been affected because of this flood. So this is also an aftermath of global warming, which is again coming from the environment's damage. So these two situations, which is one is the economic problems of Pakistan, and the other is environmental issues, which compelled me to think about doing such a article, such a research, which can open a window for sustainable and affordable energy. So our project, which is solar power plant, it would be giving us another solution to the problem which is being faced right now. Here, some statistics of the situation have been shown. On the right hand side, you can see a graph which is a generation mix of 2021, which is showing that the 59% of the produced power is coming from the fossil fuels, and the renewable is having a very little portion. Especially, you can see that solar is only contributing 1%. It means the potential is not harnessed yet, and it still has to it still has a long road to do. Wind is only 3%, so the renewable energy has a long ground to play. And on the left hand side, you can see a peak demand forecast, which is prepared from 2019 to 2047. This forecast is being prepared by the agency, by the institution of Pakistan called National Transmission and Dispatch Company, which is responsible for the power transfer to the to whole country. So they have prepared this indicative generation capacity enhancement plan till 2047. This graph is prepared on three different scenarios. One is with low GDP, which is 4.5%. Other is normal GDP 5.5%, and the third one is the high GDP 6.5%. So if we just talk about the base case scenario, which is normal GDP, we can see that Pakistan would be needing its peak demand would be more than 100,000 megawatt in next 25 years. So right now it's standing on 34,000 megawatt. So we can understand that it's an increase of three folds. So as we discussed in the last slide, so it is not sustainable for Pakistan to continue its journey as it is doing. It's neither economically viable, not sustainable, and neither and nor for the environment. So it is the need of the hour to think about the alternate and the renewable energy resources to ensure that the country's affairs are running properly. Here we will talk about the potential of solar power in Pakistan. So there are many reports which have been compiled by the international agencies like World Bank on the potential of solar power in Pakistan. So the experts are quite convinced on the fact that the potential of solar power in Pakistan is enough to address the gap and the energy demands of Pakistan by protecting the environment, by providing the clean energy. On the right hand side, you can see a graph between GHI, which is global horizontal irradiance, and the temperature, yearly average temperature. Before discussing on the actual results of the graph, let's discuss that what is GHI. So GHI is a measure of total radiations received by the ground, and it is a summation of two components. One is DHI, which is diffused horizontal irradiance. It is the radiance which is not received directly to the earth, but it is coming from the environment. And DNI is direct normal irradiance, which is coming directly from the sun in a straight line to the surface. The Z is zenith. It's an angle between sun and the zenith. Like the Z is at 90 degrees. Z is equals to 90 degrees when sun is rising and at the sunset, and it is 0 at the time of noon. So we can see that cos 0 is equals to 1. So it means that the global horizontal irradiance would be at maximum at the time of noon, and during and before and after that, and it would be 0 at the time of sunrise and sunset. So Actually, Pakistan, we in this graph we divided Pakistan into three different zones. One is the central zone, the other one is the southern zone, and third one is the northern zone. We can see that almost all of the parts of Pakistan are showing great potential to solar power, but specifically the southern part is showing very convincing results, which is an evidence of great potential of solar power in Pakistan. We have data of four different cities: Hyderabad, Turbat, Khuzdar, and Bahawalpur. So it's a long area, it's a long belt where many solar power plants can be installed. We all are convinced on the benefits and the positive impacts of solar power plants, and in fact all of the renewable energy resources. But it is also a fact that the renewable energy sources general and solar power plants in particular have its own problems as well. And some of the problems are listed here. It's the voltage fluctuation, low power quality, harmonics, high uncertainty, low fault ride through capability, frequency fluctuations, generation reserve is low, and interconnection with the grid is a big challenge. So actually what happens is that whenever there is a demand of load or the reduction in the load, so frequency fluctuations happen. So in that situation, the relays installed, which are the rate of change of frequency rock-off relays, they usually tend to operate, which disturbs the power continuity. And difference of whenever there is a difference of reactive power, so voltage fluctuation happens. So that's also not a desired thing whenever we are feeding to load, because the voltage fluctuation causes damage to the load side equipment. And because the originally power produced by the power plants, by the solar power plants at DC, and we need to install and engage many power electronics converters, which convert it to the AC power. Involvement of power electronic devices creates harmonics, which ultimately lowers the power quality. And now further to this, it has low fault ride through capability. Whenever the solar power plants gets any sense of fault, so it just disconnect itself very quickly from the main system. So this is a problem, and we don't have any generation reserve here to address the load and the generation gap whenever there is such a situation. So ultimately we need to do the load shedding on that. And last but not the least is the interconnection with the grid stations. Actually, whenever we talk about the grid stations interconnection, so at grid station there are definitely there is a power which is coming from a different source, and we are connecting a power from solar power plant. So in electrical systems, we whenever we had to synchronize two different sources, so we need to be very particular and cautious about the phase angle, about the voltage amplitude and the frequency wave between the two sources. So it is very much important to ensure that all of these set parameters match of these set sources, and then we can definitely interconnect. So while dealing with solar power plants, interconnection with the grid demands a very diligent response and a very robust design of the system, which can handle the abnormalities and ensure that the system is harmonized and the system is synchronized with the grid station. Here we'll talk about primary components of our proposed plant. We do have PV cells here. I'll be discussing about the number and the orientation of the PV cells in the coming slides. And after that, we do have maximum power point tracking controller, which is equipped with a very reliable and proven track record of intelligence. It's P&O algorithm, perturb and observation, and third one is boost converter. Boost converter's job is to get the stable and consistent output from the power plant, from the PV panels. And then obviously we deployed inverter, which is converting the DC power which is generated by PV cells. And then we have phase lock loop, PLL, and its job is very critical, as we were discussing in the last slide. Phase lock loop is taking the supply from taking the grid voltage as a reference voltage and ensuring that the DC power, the AC power which is generated by the inverter is synchronized with the grid station, so that so its phase lock loops, the basic job is to ensure that the synchronization is done, so that the power which is fed to the grid station is not creating a problem there, and it is running in parallel. This slide is also pretty much talking about the same thing which we discussed right now. So a PV system would be comprising of 64 number of parallel strings, and there would be 5 number of modules connected in series, and each would be having 315 watt. And we do have MPPT controller, which is ensuring that the PV cells are operating at particular and that specific voltage, which ensures the maximum output power from each and every PV cells, which is actually making this power plant an efficient, and which is ensuring that we are not losing any power. Here we would be discussing about the MPPT controller and its graph. Energy output of the PV cells is largely dependent on the location of the sun and the resultant sun rays direction. So any change in the location of the sun and the rays of the sun would have a direct consequence on the power produced by the PV cells. If we look at the graph of the voltage and current, so it is showing that there is a unique point where the maximum power is producing by the PV cells. So that unique point is called the maximum power point, and we can see that power on either side of that particular point, which is called the maximum power point, is not maximum. That's why it is very much important to track that specific point and ensure that the PV cells are operating exact at that point. And so that's why we need to deploy an effective and intelligent DC to DC converter, and which can use this algorithm, which is the P&O algorithm, and ensure that the output power is maximum. In this block diagram, you can see that the MPPT algorithm is actually controlling the switching of the PV panels. It is helping the PV panels to operate that specific point where the power can be maximum, and we are achieving definitely through the pulse width modulation, which is controlling the switching of the PV panels. And it's a combined unit which is called a MPPT controller, and that is helping us to get the maximum power from the PV cells. Here is the flowchart of perturb and observe algorithm, which is applied in this project. P&O algorithm is a quite reliable algorithm, and it is most widely used in the applications of MPPT and solar PV applications. This is a continuous process of observation and perturbation till the operating point converges at MPP. So if we talk about its flow chart, so the algorithm actually compares the power and voltages of time k with a sample at k minus 1 and predicts the time to approach to MPP, and a small voltage perturbation changes the power of the solar panel. If the power alteration is positive, the voltage perturbation is continued in the same track. But if delta of the power is negative, it indicates that the MPP is far away and perturbation is decreased to reach the MPP. So this is how this algorithm operates. So this is the flow chart, which is also describing the same thing. Here is the MATLAB model of our proposed system. So we can see that I can just highlight it because there are different parts. These are the PV panels. This is just a model which is displayed the actual number of the PV panels I have mentioned in the last slide. So we can say that the input to these PV panels are here. One is the temperature and the other is irradiance. So we are changing the temperature and the irradiance level to see that how much power output is changed by changing these input parameters. In the coming slides I'll be just discussing the three different cases, but right now we can see that the temperature is when we actually change the temperature and the irradiance, so the output of these PV cells would be changing. So this whole part is the MPPT, which is having P&O algorithm as well, you can see that it is coupled with the PV panels, and it is ensuring its switching and operation. It has its role in the switching and operation of the PV panels. So this whole part is the boost converter, of which we just described, that its purpose is to get the consistent supply from the PV cells. This part is inverter, which is ensuring the conversion of the produce DC power to AC power, so that it can be fed to load and the grid station. This part is our PLL phase lock loop, which is ensuring the output power is synchronized with the grid. So you can see that this is VG, which is a reference voltage which we have taken from grid. So this is how it is taking the input from the grid station, like the voltage reference is from the grid station, and then it take it as a reference, and it has its own different components to ensure that the output of the inverter is synchronized with the reference voltage signal. And then the synchronized power is fed to the grid station. So this part is then again would be concerning to the grid station. We actually analyzed the developed system, the developed solar power plant according to the actual weather conditions in Pakistan. So Pakistan is a country which usually has a longer summer and shorter winter. So we actually deployed that particular set of temperature to the power plant. Right here we do have three different range of temperatures. One is 25 degrees centigrade, other is 35 degrees centigrade, and the last one is 45 degrees centigrade. We varied the temperature, and we run the simulation on each temperature. We run the simulation separately on all these three cases and get the output, which is the real and reactive power. And we see that what is the behavior of our proposed plant. So at each set temperature, the irradiance level is also different, and we actually model the irradiance to show that to show a whole day. We can see that in an actual day. So it starts with the gradient starts with 0, then goes then starts rising and then goes to 1, and then after 1 it goes to again 0. I actually use that and use that pattern of irradiance. The system which is proposed here is actually following that days pattern of irradiance, and giving the output on that particular pattern. So on For all of these three temperatures, the irradiance level is different. 25 degrees centigrade is posing a different irradiance than 45 degrees centigrade, so that impact of temperature variation and the corresponding gradients can be seen in the output of the system. So in the coming slide we will be seeing the graphs of our output on these three different temperatures. Here are the output graphs for three different temperatures, which we just discussed, that these are our three different cases and three different inputs, and we got three different outputs for these temperatures. So we can see that at 25 degrees centigrade, it is the most it is the maximum power when it's produced at 25 degrees centigrade. It's more than 100 kilowatt, and then if we come on 35 degrees centigrade, so the power is still its output is still convincing, but it's not as good as 25 degrees centigrade. So it varies, it just limiting to around 90 kilowatt. So the least power is produced when the temperature is at 45 degrees centigrade. Coming on the conclusion of the project, the MPPT controller successfully ensured that the PV modules are operating at its maximum power point. The optimized power is ensured from the PV cells, and that unique point which is mandatory for the operation of the PV cells to get the maximum power, that is ensured. Boost converter actually does its job, and it ensures the consistent output power from the PV cells, and the PLL phase lock loop actually ensured that the power which is fed to the grid station is synchronized with the grid station. So simulation results of different parameters. So we actually change the parameters to check the robustness of the system, to check the reliability of the system, because in a real-time world the weather condition is continuously changing. So we put our proposed model into that actual situation, so that we can analyze that the plant can handle the real-time scenarios. So the simulation results prove that the maximum power is produced when the temperature is at 25 degrees centigrade, and it is in return actually where we started, that it is proven fact that most part of Pakistan has enormous opportunities and potential to generate the solar power plant, and it is quite enough to meet the energy needs of Pakistan, and it can definitely help the economic situation and the environment situation as well. We believe that the solar energy is the future of Pakistan, and it can help to provide a sustainable solution. Thank you.